All right, thank you. Welcome very kindly to all of you. My name is Abhijit Bhattacharjee. It's easier to say than it looks. And I've been an application engineer at MathWorks for 5 years. And my area is, these days, I am concentrating in machine learning and deep learning, and I have a background in computer vision and image processing as well. I'm really happy to be here today. This is my second time here at this university. And we have a great program for you today, a number of different topics. The first one that I want to go over is just an overview of machine learning and deep learning as we have achieved to this point, which is 2017A. MathWorks, we release a new version of MATLAB twice a year. So there's a A release, usually in the beginning of the year, and then a B release. So the latest version now is 2017A. So, what do we have in this new release? Well, let me give you a little background. I know Phoebe covered a little bit about the background of AI and machine learning. So AI, or artificial intelligence, used to be a very fashionable term in the 80s, and then it really fell out of fashion. People thought of it as a really old-fashioned term. And suddenly it's starting to rise again. And I think that reflects the technological progress as well. So the mathematics of AI, such as neural networks and machine learning, have been around for many decades, 30, 40 years. But at that time when they were first introduced, they were investigated for a while, but then they were kind of put on the shelf, like intellectual curiosities, because it wasn't really feasible. But now, due to advancements in technology, suddenly these mathematics are being revived and being used in technological areas. So I just want to give you a quick example of some key points in the timeline in the development of technology in artificial intelligence, machine learning, and deep learning. So I'll point out a particular instance. In 2011, IBM Watson won Jeopardy. Who here has heard of IBM Watson? Raise your hand. Okay, good. It was world famous. A few of you have heard about it. IBM Watson was a robot or a machine that was trained to win at the game of Jeopardy. Jeopardy is an American trivia game show where you answer questions. Now, their challenge was not just to answer the questions. I mean, you can Google a question and Google can answer it, right? The actual challenge was for it to understand human spoken natural speech and then respond back in a natural way as well. And so it was a famously televised event, but that was 6 years ago, that technological advancement. The IBM Watson team still exists today and in fact is doing incredibly advanced things. For example, the IBM Watson current models are being trained to diagnose cancer. And some of these units are able to diagnose cancer better than some doctors. So the fact that we are at this amazing stage of technological development is just, we live in a great time. It's a very exciting time. And so, and then we're going to see how deep learning has advanced things even more. So, how many of you here have a background in machine learning? Please raise your hand. Who here has studied machine learning or has used it? Okay, a few. That's okay. Actually, I think I saw 4 hands rise, and that's very typical for my audiences. So I'm happy to see that because this is actually one of our key movements in this era, and that is machine learning has been developed by a handful of specialists, but now it's so useful that we want to be able to use it in all sorts of domains. Most of you here are engineers or scientists or mathematicians and not necessarily experts in data science. But data science is so incredibly useful that you would like to be able to, I would like to be able to make use of it. And so one of our key messages or one of our key strategies at MathWorks is to enable anybody to be able to use the best algorithms that are out there, which are in data science or in machine learning, even if you're not a domain expert. So machine learning and deep learning, we're going to talk about it all throughout today. But before I do, I just want to give you a caveat, and that is, machine learning and deep learning are not always the best solution for your application. Consider carefully if you really need to use machine learning and deep learning. They're very powerful tools, but they're not always the right tool. So when are these tools the right tool? So let's look at some scenarios. One example is if the problem that you're trying to solve is too complex for handwritten rules or equations. So if you want to do, say, speech recognition, and you want to analyze a speech waveform and then figure out what a person is saying, think about how difficult it would be to write a set of rules or decision logic to determine what the person is saying. It's almost impossible. The scale of the problem is immense. So that's an area where learning, machine learning by itself, is useful. Another aspect would be if you have a problem that needs to adapt to changing data. All right, so we have lots and lots of applications where if you had a human updating all the time, it would just be basically grunt work for a human just to keep updating. That's something that where machine learning really shines in the areas where data is ever changing. And then lastly, one other scenario would be when the program needs to be able to scale. There is a point now at which, actually I was reading this article, it's very interesting. It said something like, in 1996, the total data transmission around the world was less than 100 gigabytes a day. Think about that. You and I probably downloaded 100 gigabytes every week at this point. This is the total throughput of the entire world. Only 21 years ago was 100 gigabytes a day. And so the explosion of data today has necessitated the fact that we can no longer have humans read and analyze everything by hand. And that's another area where machine learning is essential, because you can very efficiently comb through large data sets. So I know that there are a lot of people here who are new or unfamiliar to machine learning. So let's talk about the process. This is the overall process, and we will see many examples throughout today of how we facilitate machine learning. The first thing in machine learning is always, how do you access and explore data? How do you bring in your data? So if you're designing, let's say, an object recognition algorithm, you would need to teach the machine how to recognize objects by providing examples of objects. So you would need to provide lots and lots of videos or images. How do you access that data? If you had to analyze, I don't know, 300 million entries, like, for example, the Netflix video service. It's known for being one of the best recommendation engines in the world. It knows what kinds of movies you want to watch before you know it. How does it know? Because of all the data that was provided to the engineers. And so how would you analyze and access 300 million records of customer transactions and data? Write a giant for loop. That would be inefficient. So we are going to talk about efficient ways to access and explore data. But once you have the data is not all useful, and it doesn't all carry meaningful information. So the next stage of it would be to pre-process and clean the data, or to extract meaningful features. This word features is something we're going to talk about all throughout today. Features are pieces of the data that carry a lot of information. And so that is actually one of the most difficult steps, or most time-consuming steps, in a machine learning environment. In fact, just this first part alone of accessing and pre-processing data accounts for over 80% of a typical engineering effort. Finding the right features is one of the most challenging things. After that, when you have the right features or the right data, you can then develop predictive models. And this is where the machine starts to learn from examples of previous data. And you can choose all sorts of different predictive models. And then finally, it's all very, very good to do in MATLAB or another programming environment, but then having it to deploy it into a system is another challenge. So taking an algorithm from your prototyping environment and then going into your analytics system. We provide lots of tools to do that as well. So here's some examples of how we handle these things. So we have new data structures for enabling machine learning with big data. We have ways to select useful features rather than process all of the raw data. There are ways to compare and fine-tune models so that you can quickly optimize them for the best performance. And then we also have ways to deploy into embedded systems and other areas by generating models that can go into other environments. We'll talk about that as well. So, who here is doing deep learning today? Okay, a few of you. Who here is using Caffe? Who's using TensorFlow? All right. So these are the most popular frameworks that I notice out there. So a few people know what deep learning is, but most of us here are new, or at least we've heard the term, but maybe don't know exactly what it means. It's like all of these popular terms, like big data. What's big data? What's big to you? Some people will say, I don't know, a book is big data. When I was in college, I always, all my books were big data. I was never able to process my books. But some people would say 100 gigabytes or 100 terabytes, or it depends. It's all kind of dependent on your idea of scale. So deep learning is also one of those ambiguous terms that people don't really understand, but I want to make everybody familiar with the terminology. And so deep learning is a subset of machine learning. We just talked about machine learning, so here's another illustration about machine learning. So an example of a machine learning algorithm would be if you are deciding, if you're doing a classifier. So if you have an image of a vehicle, you would first extract features manually. You would have to decide and engineer what these features are. You would then decide the classifier, and then you would get an output, which is like that, like a car. But deep learning is a little different. With deep learning, you get to skip a few steps. Instead of manually choosing features or manually designing the data pre-processing steps, you get to just feed in raw data and then get back an output, which is your classification. Everything inside here, the features are automatically learned and the model is automatically learned. That's what's so promising about deep learning. We call it end-to-end because of that. Because you put in input and you get an output and everything else happens in the middle. That's one definition of deep learning. We'll talk about some others. But this is one of the key aspects that differentiates the traditional machine learning from your deep learning. So looking at this, thinking that, well, I can skip some steps and not have to do manual feature extraction, that sounds really good. Why would I ever use regular machine learning? Why don't I always use deep learning? Can anybody think of some reasons? I think if you think about it, some people here are familiar. Deep learning, if you think about the word deep, that implies that the computation is going to take a lot of time. So that's one aspect. Machine learning techniques are still far, far faster than deep learning. And also, they don't require as much data. you need a lot of data. Deep learning algorithms are very, very greedy for data. They usually perform better and better when you feed more and more data. So there is a time and place for both of these types of algorithms, which is why when we're talking about machine learning and deep learning today, we're going to talk about both aspects. And we'll talk about instances where deep learning versus machine learning could be better for your application. Okay. So I mentioned that it's end-to-end learning because you learn directly from data. Now, what is an example of a problem that deep learning can solve? So I took this video that you're about to see on my laptop. I attached a camera and ran MATLAB while we were capturing this video. So I'm pointing my camera at various different objects, and you can see the labels. The labels are incredibly good, actually. Backpack, mouse, and with high confidence levels. We're using a deep learning algorithm that's recognizing these objects. But it's so many different types of objects. Sunglasses, even chainmail. Who knew that we could recognize chainmail? And goblet and red wine are both very reasonable categories for that object. And then you can classify that, beer bottle. The fact that one single network can classify so many different types of objects, and they're so diverse, should be highly impressive to everybody. And this isn't even new technology. This is from 5 years ago. And the reason that deep learning, you can see why deep learning has become such an amazingly fashionable and high-tech area that people are just captivated by. This one network is running a classifier that can categorize 1,000 different categories. And it's operating in real time. On my laptop, it was operating in real time. You saw it. Now, how do we begin to develop such a network? How can you even begin to get to the point where a single tool can recognize all these different things? It first necessitates a concentrated effort in terms of both data and a task and a measurement. So we need data, we need a task to perform, and we need some sort of way to measure it. And about 7 years ago, this organization was formed called ImageNet. It was formed by a number of researchers around the world, such as Princeton University and Berkeley and others. The researchers got together and decided that they needed to create a publicly available data set to accelerate the development of computer vision algorithms. So, who here has heard of ImageNet? Please raise your hand. Okay, good. A few of you. For those who are not familiar, ImageNet is a publicly available database of 1.2 million images that are hand-labeled into 1,000 different categories. So here's just a quick sample. And in fact, I was watching the TED Talk by the person who founded ImageNet, and she was saying that at one point they were employing 46,000 people around the world to label all these images by hand. Okay? You can think about how expensive and time-consuming that process was. And when they made this data set available, they started an annual challenge every year to challenge the world, anybody, meaning research organizations, companies, or anybody, to come up with the best algorithms for these tasks: object recognition and object localization or detection. So finding where the object is and what it is. So one of the most famous tasks is the object recognition task, which is what you just saw when I was using the camera example. And if you want to compare the best algorithms in the world, we need some sort of measurement, and the measurement that's used is the top 5 error rate, which I will explain in the next slide. So this is a challenge that runs every single year. And the winners of the challenge become famous in this community. Winners of this challenge in the past have been models such as AlexNet and GoogleNet and ResNet. You've heard of these terms, most of you. So why is deep learning so popular? I think many of you know some of the reasons, but let's clearly lay them out. First is, of course, the results. These algorithms have accuracy beyond comparison for the task that they're doing. You already saw an example. So this graph on the right is an interesting chart. This is the top 5 error on ImageNet, meaning that in the 1,000 categories, you had to predict successfully the correct label of the object within the first 5 categories of your prediction. And so if you didn't, that was considered to be an error. And so in the first year of this challenge, the best algorithms in the world were getting 30% error. And that was considered a good result. And something interesting happened 2 years later, which you have this immense drop in error, and it's around 15% at this point. And that was the introduction of the first deep learning algorithm, which is a convolutional neural network, CNN. And in this case, this first CNN was called AlexNet. And because it was so amazingly good at doing this job, every single winner since then has been a deep learning algorithm. And 2 years ago in 2015, the best algorithms in the world surpassed human level performance. So that's amazing. Another reason that deep learning is now popular is because of the availability of these immense labeled data sets. That's something that wasn't around in the 1980s when they first came out with the math. Now there's all sorts of data available, but not just data, labeled data. And these are publicly available for free. That has caused a lot of advancement in this technology area. And it's not just ImageNet, there's also others. Then the other thing is now we have computing power. Because of GPUs and other accelerators, we have the ability to compute all this on all this data. And then the last point that I want to mention is a little bit strange, but I call it bootstrapping. And what I mean by that is, deep learning is the only field that I know of where you can start out by using the best available research as your starting point. If you were to do just traditional machine learning, you have to make all the decisions yourself and start from scratch. In deep learning, you can use the best solutions from the best researchers in the world. And that means you can start prototyping with the best available solutions. That is, the efforts, the years and years of effort of the best AI researchers in the world who have achieved this level of performance, you can just start with that and then go from there. And we will talk about that. So I'll just talk about a few other new things now in MATLAB, because the landscape of machine learning and deep learning is such that we have seen the trend at MathWorks, and we are investing heavily in it. Now that we all can see it, and at MathWorks, we made it one of our biggest priorities to support people who are doing machine learning and deep learning and big data. It's one of our areas of heaviest investment, and every release, that is 2 times a year, we're coming out with a huge amount of new features that allow you to accelerate this process. So I'm just going to go through a list of some of those features. So around 2 years ago, we created this app called the Classification Learner. We've had machine learning capability in MATLAB for a long time, maybe 10 or 15 years. But people didn't know. People didn't know that we had that functionality. So we made it much more discoverable. We made it easy to find through this app. And then we've made improvements over time as well. We have parallel computation for machine learning. We also can support big data. And an interesting topic as well, which we will talk about today, is you can generate C code for a predictive model. And then that way you can use it in an embedded system. And then in the latest release, we've also created easy-to-use functionality for regression, which is another type of machine learning. Classification is to find what category is an object. Regression is to predict a number, like what is the temperature going to be tomorrow? That's a regression problem. And in the deep learning space, we've made a huge number of improvements as well. In our neural network space, we have convolutional neural network architectures. We can use pre-trained networks, and we provide a number of famous pre-trained networks that are really good starting points. Our tools also can access out-of-memory data. Phoebe mentioned this earlier, and we'll talk about that more. We can also easily take advantage of multiple CPUs or multiple GPUs when training these networks. And we can also import models from Caffe. So, I'll just close out with one other aspect, and that is we have a huge amount of strength in the computer vision area. Our tools have been known for computer vision for quite a few years now. And we've added 3D point cloud processing as well as deep learning frameworks for object detection. So these are the RCNN algorithms. And we will talk about those as well. All right. So we have 2 or 3 minutes left. Are there any questions before we move to the next session?
当然有没有问题？我们今天有提供礼物送给大家，所以如果有问题，我们都有一份神秘礼物。有没有人要问？
Yeah, we have prizes for you too. If you ask a question, you get a prize. Yes.
You mentioned that it costs 80% effort in the to access and explore data and reprocess data. Do you suggest that MATLAB will help you to reduce the effort?
Okay, great. Yeah, great question. 80% of the effort is in pre-processing data. And yes, exactly that. We have a lot of tools to reduce that effort. We're going to talk about that. And so you'll see examples for actually all throughout today's session. We'll do multiple examples of that. Other questions? Okay, we'll just move on then. We'll have a few extra minutes for Q&A later. All right.